Okay, my apologies for small technical error, and but we are going to be starting up again here, and I would like to introduce Elaine Hepley. She's the data analysis manager for Polaris, and this is going to be an awesome presentation on new techniques in Varnish. So, without further ado, Elaine, we'll see if this works this time. Here we go. Take it away.
Thank you so much for the warm introduction, and welcome everyone. I'm excited to share with you new testing techniques in varnish analysis. A little bit about myself. I manage a team of 12 analysts at Polaris Laboratories. I specialize in varnish analysis, and I'm very passionate about the analysis and varnish testing. I have been with the company 14 years, and I am also STLE, OMA, and CLS certified, as well as a part of the committee, and I'm currently the chair. Aside from that, I am bilingual in English and Spanish. What we're going to be reviewing today is a quick review of varnish, what causes varnish to form, testing for varnish, micropatch analysis and its benefits, as well as correlation between MPC analysis and micropatch, and then the new introduction of our new MPC testing. So what is varnish? Varnish is a gel-like, sludge-like substance that adheres to a lot of metal surfaces. It can be a heat insulator. It can be very gummy-like, where it can absorb a lot of abrasive particles. As it continues to circulate within the system, it can generate wear. It is a lacquer-like substance. Varnish comes in various different colors. It's kind of like that term, not all varnish is created equal. What causes varnish to degrade? Basically, it's a result of oil degradation over time. That is what causes varnish. Static discharge, dieseling, hot spots, gas, water, fluid incompatibility. For example, if you have a PAG mixed with a mineral oil, that can significantly impact the varnish formation. Aside from that, we can have oxidation of the oil degradation. Solid particles can attribute to that, and also thermal degradation. If the machine is operating at much higher temperatures, it will cause the oil to oxidize at a more rapid state, causing varnish to form. And lastly, contamination by wear and pressure can also impact varnish. So where does varnish appear, one might ask? Well, oil degradation byproducts that are solubilized. You will see it in turbines where it would cake on or bake on to the surfaces. We've seen it on the spools and the valves. We've seen it in the cooler areas where it's the heat exchangers. You'll see it adhere to the cooler spots, and that's where it will also form. So you'll see a lot of that varnish all throughout the system. So what detrimental damage can be caused by varnish? It will cause the valves to clog and seize. Filters with small passageways will get also clogged as well. I have seen varnish where it's a very sand-like, grainy-like material, and as that's being filtered through the system, you will see that the filters will get clogged with that. And I have some images to share with you that will show that. Valve sticking, which leads to trips and fail to starts. We have shorter oil life. As the oil begins to oxidize, that varnish begins to form, that oil isn't going to last as long as it normally would. You're going to have a loss in production. You're going to see your filter get blocked. Ineffective heat exchangers. Because varnish loves the cool zone areas in the systems, the heat exchangers are the ones that get impacted the most, and then they have to work double time as well to keep the oil cool. It can also cause a sandpaper-like surface as well. As varnish goes through the thermal degradation process, it does create a thin layer, like a layer of paint per se. It's like a lacquer-like that hardens over time, but the surface of that can be very abrasive and can be very damaging to the system. Where does varnish take place? Initially, it started with turbines more than over 30 years ago, and with time, we have seen it happen in compressor systems that are compressing very high hot gas, hydraulic systems, and cogeneration applications, or in gas turbine applications that are electronic hydraulic control systems, is where you will see varnish form as well. And any kind of large circulatory lube system, you will see varnish form as well. How do we identify varnish? So there are several different things that you can do that are field tests to help with that. Oil discoloration, you will start to see the oil be like a light yellow, clear, amber color, and over time it will darken to like a reddish, amberish color, brown. You can smell the burnt smell. You might see high particle count results. So if you have been actively filtering your system, but you're not seeing your particle count results decrease, that might be an indication that you might have varnish that's solubilized in the oil. Increase in acid number. The same with oxidation. As you see acid number increase, you might also see oxidation. They do correlate with one another. Increase in temperature. You might see your sensor temperature gauges increase. I highly recommend heat gun sensors to be applied or routinely used if you suspect varnish in the system. And lastly, low antioxidant levels that are going to be mainly detected through ruler analysis or FTIR analysis, and we'll dive deeper into that here further. So now we're going to talk about testing for varnish, the various different types of test methods that are out there. The traditional one has always been MPC, membrane patch coulometry. This test detects insoluble varnish in the system once it's plated out. Ruler analysis will check for the antioxidant levels depletion. So primarily looking and focusing on two different types of antioxidants. We're looking at amines and phenols, and a lot of turbine oil formulations will contain both or might have predominantly one over the other. Then we have RPVOT. The RPVOT measures the remaining useful life of the oxidation stability of the fluid. So when you are less than 25% of minutes or remaining useful life is when you will see a depletion significant enough that varnish would probably start to form at that point in time. FTIR analysis is very useful for detecting the degradation of phenolic content. In some formulations, the phenols can change in chemistry and become acidic at that point in time. FTIR and ruler are very helpful in that detection and reaction that takes place in the lubricant. Micropatch analysis, believe it or not, has also been a form for us to detect varnish formations in different systems where we normally wouldn't be able to pick up on that through our standard testing or traditional MPC or varnish analysis test. And then lastly, we have also picked it up through our filter debris analysis. We have been able to flush out varnish formations that have been captured in the filter media, and we end up seeing that underneath the microscope tests. So let's take a little bit of some time to discuss more in detail about varnish potential testing. The primary test for varnish potential has always been the MPC, ASTM D7843. It indicates how severe the potential for varnish is. It is also used and coupled with secondary tests like ruler and RPVOT, which you can correlate all three to monitor the antioxidant level of the oil and also check to see as the antioxidants degrade, are we starting to see MPC value increase? Both tests can indicate a lot of things: the potential for varnish, if varnish is there, and how we can mitigate or remove it, or the severity of the varnish. So the one thing that is very useful is that, but it cannot tell you the specific type of varnish that's forming. And that is something that is very key and crucial when it comes to understanding the type of varnish and how are you going to be able to remove it. They also cannot tell you if you have insoluble varnish or soluble varnish? Well, it will detect insoluble. Let me correct myself. It will not detect soluble varnish and how severe it is. So here are the 3 different types of tests that I would like to review with you guys. The first one is ASTM D7843, which is our traditional MPC. The second one is our new SMPC testing technique, which is done in-house. And then lastly is the micropatch. So insoluble varnish is our traditional MPC method. Our soluble varnish is going to be our SMPC technique. And then the varnish shape or varnish formation will be your micropatch analysis. All 3 will be able to indicate how severe and the various different forms and stages of varnish that you might have in your system. So let's talk about insoluble varnish. It shows when the varnish has collected after the filter, after heating and cooling, when we wash it with the solvent. So basically what we do is we heat the oil for 23 to 25 hours at 60 degrees Celsius, and then we take it out of the oven. We take 1 oil drop and then we set that aside for the soluble varnish, and we'll jump into that here in a minute. What we then do is we take 50 mils of the sample that has been in the oven, and we put that into the dark for 3 days. After it's been in the dark for 3 days, then we dilute that with 50 mils of PET, and then we wash it off with heptane and then let it dry and then take a reading. That's where we get our MPC color reading. Aside from that, we are now able to detect and report the LAB values. I'm going to talk a little bit about what each value means and how that can help correlate what the cause of varnish can be. The L value is the black and white scale on the color spectrum scale. The high L value shows the possible value of soot particles, microdieseling, electrostatic discharge, or hot spots. So that's a good thing to keep in mind. The A value is the red to green scale. A high A value is greater danger of sludge building, corrosive particles, or diminish extreme pressure additives. This is something that you do want to monitor if your turbine oil has some type of EP additives. You definitely want to monitor the A value for that. Your B value is going to be on your yellow to blue scale. So a high B value indicates that the oil is more susceptible to sticky deposits, more granular information to give better indication of root cause. So you might see some gummy-like, orange-like tinge to the MPC. That can be indication that your oil is susceptible to sticky varnish formations. Now we're going to talk about soluble varnish. This is a brand new technique that we have created. And basically what we do is after the oil has heated for 23 to 25 hours, we take an oil drop and then we place it on the patch. We immediately then put it into the dark and let it dry for 24 hours. Afterwards, we take a reading, a color reading of that varnish on there, and then we also report the LAB values. Here are some examples of the correlations that we have found with insoluble and soluble varnish. So the first images to the left, we're going to see that the IMPC value was 7.7. We had a high L value at 95.1, a value of 1.7, so that indicates to me that EP additives were okay. B value, we're at 5.9. We're not going to be too concerned with any gummy deposits. The varnish patch looks pretty white, pretty good. We're seeing a little tinge, but not that bad. The SMPC value, we're at 16.1, which we're still pretty good. No severe indication of varnish formation. The L value is at 96.1. The A value is negative 0.9, and the B value is at 15. So we're looking to be okay in that retrospect. The next set of images on the right-hand side will show a very interesting correlation. So the IMPC value is at 18.1. We begin to flag SMPC or IMPC at 15. So that's a severity 1. We're looking to see that the L values are at 86.8, the A value is 1.2, so we're looking okay, and the B value is at 12.1. If you look at the IMPC patch, you'll see that there's some grayish discoloration to the patch. The SMPC value, however, shows something else. It is much higher. It's at 34.2. The L value is at 82.9, and the A value is at 0.6, and the B value is at 29.5. So that can be an indication that, one, we might have a microdieseling issue, and number two, this oil more than likely has the potential for sticky varnish deposits. Now we're going to talk about the micropatch analysis. What is a micropatch, one might say? Micropatch is a 0.8 micropatch filter that captures yellow metals, non-ferrous wear, soft particles, and filter media and varnish. This analysis provides an insight to the type of varnish that's in the system. Also can tell you more about the type of regime. Different types of contaminants can also be captured that we normally wouldn't be capturing through our standard testing. Microdieseling. So here is an example of what a micropatch analysis and varnish patch can share and highlight some more. The patch on the left-hand side is very gray in color. That's an indication of microdieseling taking place. So I had a customer reach out to me and let me know that there was a failure on the steam turbine in a nuclear plant out in Europe, and they needed to know if the crystal-like or clear-like formations that they found was varnish. So I recommended doing a micropatch because our standard varnish analysis tests weren't highlighting anything additional. So the image on the right, you will see clear varnish agglomerations that are encapsulated. They have encapsulated carbon molecules. Within those carbon molecules, we also detected wear debris embedded within it. This was mind-blowing because it was able to determine the detriment of microdieseling varnish that generated wear and ultimately led to failure. Varnish agglomerations and abrasive. So I kind of wanted to highlight some different varnish formations that have been detected through micropatch to show its benefits. On the right-hand side, we have a gummy-like varnish agglomeration that, if you pay closer attention, there is some debris around it. As you can see, it has absorbed some of that grainy-like, sand-like material, those contaminants, and as that is circulating in the system, it's going to generate and attribute to wear. The image on the right-hand side shows how the varnish can start off with microagglomerations, can be translucent, and over time, they tend to get hardened and then form that layer that can bake onto the surfaces of the system. Here are some different images of varnish flakes that would typically break off once they have been baked onto the surfaces. The image on the left has been a varnish flake that's been exposed to high temperature and has changed color over time. And the image on the right is the beginning stages of what varnish will look like and then begin to harden. Here we have some crystallized varnish flakes. As you can see, the image on the left has like a very sand-like, desert-like appearance to it. That's an indication of a lot of microagglomerations and sandy-like varnish that's generating into the system, which can lead to filter clogging. And then my favorite, the lacquer-like nail polish appearance. That is the beginning stages of varnish. This is where it would be very easy for you to remove varnish. The image on the right is what the varnish will transform to as it has been exposed to high temperature and has continued to evolve over time. It begins to harden. Here are some wear particles that we were able to detect, which is very important to see that because varnish does generate wear, and we have been able to discover that through MPC and micropatch analysis. I also wanted to take some time to share with you some of the questions that I always get. Can varnish be prevented? There are a lot of things that you can do to help mitigate varnish and keep it at bay. However, studies still are out there that can show whether or not varnish can be prevented. But here are some tips for you, and I hope that they are helpful. Have a well understanding of your equipment. Get to know the owner's manual, the manufacturer's manual. There's a lot of information that's on there about the maintenance and the care that is needed for that component. Ensure that your equipment is well grounded. I cannot stress this enough. Ensuring that it's well grounded and that you have the proper anti-static filters installed in your system, because static electricity can cause varnish to form. Ensure that you have the proper lubricant for the component, the operational environment, and also that is compatible with your seals. Check your sensors. A routine check of your sensors is going to be extremely important. Not only that, your pressure gauges, your thermostats, looking for loss of pressure and an increase in temperature can be an indication of varnish formation. Visually inspect the oil for any discoloration, or occasionally use a borescope to check for varnish falling out or plating out. If your MPC value is at a severity 1 or 2, that's where you want to be proactive and start monitoring that. You also want to check for any burnt or oxidized odor using thermography for hot spots, checking to see if your varnish is plating out and agglomerating. Thermography is going to find those hot spots, and that's going to help you. Vibration analysis is also a key analysis or field testing to do to check for any bearing wear, misalignment that might be going on, or if a bearing is failing. And lastly, filtration system that is applicable for the system, but also for the operational environment as well. So that does it for today. Thank you for joining us, and I look forward to your questions. Have a great day.
Well done. That was awesome. All right.
Thank you.
Excellent. Well, thank you. And I'll just share a couple quick comments here, and then we'll actually get to a couple questions. Sonia said, lovely. Vanda, thank you very much from Qatar. Our customers mostly find varnish on bearings. But we have a question here coming up. This is from Jacob. So does Polaris have plans to integrate equipment heat sensor data to see how this correlates with MPC or acid number results? Interesting.
In the future. So we currently have a service called Data Connect, where we can connect to the CMMS systems of the customers, and we're looking to advance that technology. So basically, their data feeds into our systems, and then we pull that data. So it's a push-pull system of data information. And what we want to do is eventually be able to obtain sensor data or telematic data and be able to correlate. So if I get a temperature gauge or a thermostat increasing, the other test that we're going to correlate is, are we seeing an increase in acid number? Correlate with that. Are we seeing oxidation jump? Are we seeing viscosity increase? Things like that are the wave of the future where we would like to go. So we're working on that. It's around the corner, maybe a couple years out, but that's kind of what we're looking to do to better service our customers and provide better reliability.
Very good. Excellent. All right. And several other very good comments as well. Excellent presentation. Very good. We do have a comment here from Eric saying that to treat varnish in their critical equipment, they added mobile solvencer. I think actually there's a presentation on mobile solvencer.
Yes.
So that I think is coming up here shortly.
Yeah.
And I think in Qatar they've also used a cousin to mobile solvencer. So great comments. Let's see. I have varnish in hydraulic oil. So let me. Here's a question from Musa. Varnish in hydraulic circuit causes sticking valves. The oil's been replaced completely, but the sticking issues still exist. This is such a common question, so I'm so grateful that someone asked this. So, what are your thoughts on this?
Well, my thoughts is we haven't gotten to the root of the problem, because what happens is if you're not cleaning the system and removing the varnish fully, by just removing the oil and not removing and cleaning the system of the varnish, basically what you're doing is that new oil over time is going to be contaminated with varnish, and the whole cycle starts. So one of the key things that I like to recommend to customers is, what is a root cause? Find what is causing the varnish to form and then mitigate it and then you can flush it, remove it. And if you're going to use a cleaner, if you have varnish that's caked on and needs to be dislodged, just making sure that you follow up with a thorough flushing of a neat, clean oil to remove as much of that cleaner and there's no residual from that as possible, so that when you do put in your new oil, it's in a clean system. There's no residual of the previous maintenance, no residual of the varnish, and then you can continue from zero from there. But if those steps aren't taken, then you're going to eventually, continue that cycle until you remedy the issue. Would you like to add anything to that, Greg? Did I cover anything or anything?
No, I think that's perfect. No, I always use the analogy. You don't want to take a bath in a dirty bathtub. And so you don't want to put brand new oil in a varnish system. You need to decontaminate and flush it. It's,
yes.
But yeah, that's very good. Okay, we have another question here. This is from Alona. When interpreting analysis results, which of the two, insoluble or soluble patch results, is used for caution flags?
Yeah, so usually what we want to do is varnish is a precursor when it's soluble. So that's when it begins to form in microagglomerations and it's suspended. So you're kind of okay, but if you can detect varnish at that early stage, just imagine how much savings you would have if you're able to remove it when it's soluble. So that's kind of my goal, is to help you guys, help our customers save money, save downtime, save on having to change very expensive oil, because let's face it, turbine oil is not cheap, very expensive. And we're talking thousands, hundreds to thousands of gallons of oil that are impacted. So we want to detect it early on. What we have found is as varnish, the soluble varnish starts to increase at 40 or 50, we also start seeing the insoluble varnish increase as well. And so once you start seeing your insoluble varnish begin to increase, that's an indication that you need to take immediate action to try to find the source and try to mitigate varnish as soon as possible before it starts to face problems and then you have a failure. So around 30, 45 is a condemning limit, but when you have a value of 30 is when we begin to caution.
Okay, excellent. And yeah, I think Chuck actually had the very similar question about the rating scale of soluble versus insoluble. So we have time for one more question here. So let's look at, this is from Mahmood. If there's high varnish, will this affect the ruler test, or is it not related?
Yes, it will actually, because the antioxidants are there to help against oxidation formation. That's why, they've been dubbed the antioxidants. So one of the things that we have seen is as those values diminish over time, we do start correlating that with the MPC value and start seeing an increase. So there are more studies that we're doing. We have, since the rollout, obtained a robust database of lots of data sets. So we're in the middle of reviewing our data and we're looking at adjusting our flagging and being more prescriptive. So there's always more room for improvement in our realm, and we're excited to what's going to happen next and what the future holds.
Wonderful. Well, actually, there's some other questions too that we just don't have time to. So we're gonna have to end this, but please feel free to reach out to Elaine directly. And as you can see, she is a wealth of information on this and an absolute expert in this area. So thanks so much for your contribution, and this was just awesome. Thank you.
Thank you, guys. Have a great day. Thanks for joining my session. I appreciate you. See you guys.
Great. Bye-bye.
Bye.